Hey, welcome back. All right, so yesterday we went over 7.2, the first half. So here we went over the definition of the Laplace transform, which remember is integral from 0 to infinity, so it's an improper integral. And then what we did is we talked about just basically, we went through the process of evaluating the Laplace transform on, say, the function 1, e to the at, and also sine of bt. Now, these are actually going to be the basis that we're going to build the rest of our table off of. And later in 7.3, we're going to talk about a lot of properties of Laplace transform, special properties of Laplace transforms that we can go ahead and use to build off of those three functions to make the rest of the table. And that'll be a fun little exercise. On the exam, you will have tables. So you'll have the tables of Laplace transforms, you'll have tables of special properties, and except where I ask you to do things explicitly from the definition, you'll actually be able to use these properties. I really recommend that you study how to do it from the definition though, because I'll probably ask you to do it for, say, sine or cosine or e to the at or something like that on the exam. And so you want to be prepared to be able to do that. That means reviewing integration by parts, solving for the integral, methods like that. And that's all covered in the last video. So if you are shaky on it, go back and review it, watch it again, and if you're still not sure, go ahead and Canvas, post in our discussion like I recommend. Okay, so what are we doing today? Well, there's a few special cases that, where we have to use the definition of Laplace transform, and that's going to come in when we talk about things that are like piecewise continuous. So you'll have functions that might have some jump discontinuities, and you'll have to split the integral around those. And when you do, you get slightly different looking sort of results, and you can't use the table explicitly for those types of functions, so you'll have to go back to use the definition. Piecewise continuous functions, they do come up a lot in actual applications. You'll see things like switch systems and questions about switch system stability come up, and I will never ask you how to do it in this class, but being able to split the definition of the Laplace transform across these jump discontinuities will help you be able to understand how you would approach this problem in something like a linear switch system or something like that. There are a lot of other tools that people use in those cases, and so you might not necessarily use this. I have seen researchers try to use it this way, but they totally garbled it up, and I was reviewing a paper and I just had to recommend rejection because they didn't actually get the switch systems idea right. But basically, if you really learn how to do with these jump discontinuities, you should be fine. Sorry. Getting over being sick. Okay, so what else are we going to talk about? So we're not only doing discontinuous functions with jump discontinuities where we have to split the integral over several pieces, but we're also going to be talking about when we can expect the Laplace transform to exist. And so there's a special kind of function that we're going to be talking about, and that's basically a function that can be bounded by an exponential, and we call this a function of exponential type. So basically it's going to be the absolute value of their function is less than or equal to, say, some constant times e to the alpha t for some alpha. And whenever you have a function of this kind, then you can use the comparison test to basically say that you are guaranteed to have the existence of your Laplace transform past some point. I think it's generally past alpha or something like that. Just like what we saw with e to the at, we saw that the Laplace transform is well defined whenever s is bigger than a. And so for a function that is of exponential type with type alpha, then we know that the Laplace transform is going to be well defined whenever s is bigger than alpha. So this ends up being kind of important. So talking about the inequality that you have there, the absolute value of f of t is less than or equal to e to the alpha t. This is, another way we would write that is we would say that f of t is big O of e to the alpha t. So we would just hide away the m and we just assume that something exists, that there is an m that fits this. So I'm just mentioning this because if a lot of you guys are in computer science, and so if you go on to algorithms, you'll have these sort of comparisons which are called big O comparisons. And it's basically whenever you can write this inequality times some constant. So example of a book that you're going to see that sort of thing come up in would be, say, Donald Knuth's Theory of Computer Programming. So whenever he's talking about algorithms in this book, he has big O notations whenever he's talking about timing and whatnot. And I don't know if I can find anything in here, but yeah. Yeah, we'll just leave it at that. So it comes up in computer science, and this is the textbook that you'd end up seeing. Okay, so one last thing before we go. I want to emphasize that you don't have to be of exponential type to have a well-defined Laplace transform. Really all you need to be is you need the function to be what is called absolutely integrable, and then you'd actually be fine as far as having a convergent Laplace transform. So there's some of these examples where you could basically have a function that is 0 for most of it, but then has like these triangle peaks that go higher and higher, and those peaks can go as high as you want as long as you don't let the volume of the triangles get too big. So you basically like shrink the triangle down in width and then bring up in height, and as long as the areas of those triangles converge, then you know, that function that represents those little triangle peaks will actually have a Laplace transform. This is a great little counterexample to have in your toolbox, especially if you go on to do something like nonlinear controls, because that gives you an example of Barbalat's showing that you can't really loosen any of the requirements of Barbalat's lemma, which comes up when you're trying to show a system is stable. And so, but yeah, maybe that's a little bit too deep here. But basically, what would happen is in Barbalat's lemma, you assume that you have a function that is uniformly continuous, which means it has, like, say, a bounded derivative or something like that. And so those triangle functions end up having a bounded derivative, and it fits the rest of the requirements of Barbalat's lemma is absolutely integrable, and is differentiable, and etc. And but that function doesn't go to 0. Right, which is the whole point of Barbalat's lemma. Anyway, so I guess I'm rambling at this point, and you really want to see some examples for what we're doing in the rest of the section. So I'm going to go ahead and stop here, and we'll switch back to the notepad. All right, talk to you in a minute.
Okay, so let's jump into it. So here, again, we're in section 7.2, and we're wrapping it up. So we're going to be talking about piecewise continuous functions, and also even with jump discontinuities. I guess we can also talk about some special cases where we have sort of asymptotic discontinuities, but let's keep it simple, and we'll just keep to these two for the sake of this class. The rest just comes down to whether or not it's integrable. So, for instance, you could do a lot of these same techniques if you take a look at 1 over the square root of t, and that has a Laplace transform, because the integral from 0 to infinity, or well, not 0 to infinity, that doesn't actually work out. But let's see. But if you make a piecewise continuous function, anyway, I'm rambling. So yeah, we're going to be talking about piecewise continuous functions and functions with jump discontinuities. Okay, and then we're also going to talk about functions of exponential type. So these are going to be functions that are like this. So f of t in absolute value is bounded by m times e to the alpha t. Traditionally, these are actually called functions of exponential type. For some reason, the book uses the terminology exponential order. Order usually means something else, but that's fine. Exponential type or order, we're not going to have to deal with both of those concepts at the same time, so call it what you like. For us, that means this. And in this big O notation I mentioned before, this is basically saying f of t is equal to big O of e to the alpha t, right? And that comes from this sort of big O notation. But don't worry, you won't ever have to really think about this for this class. Okay, so let's go ahead and talk about Laplace transform of a piecewise continuous function. So we have for instance, f of t could be equal to, let's choose something a little bit different from the book so that you can get some experience. We'll just say e to the t for 0 less than or equal to t less than or equal to 1. And we'll say will be a constant on the inside, so we'll have 1 less than or equal to t less than or equal to, say, 5. And then wrap it up with something like t minus 5 for t greater than 5. Okay, so what does this look like? Well, we can graph that really quick. So e to the t for 0 to 1. So basically from here up to here is going to be an exponential, right? And it's going to stop at e. So it's at 1. Then from 1 to 5, we're just a constant 5. 5 is bigger than e, so I'll just put it up here. Whoop. There we go. And then from here, t minus 5. So at 5, we're just going to be at 0, and it's going to go like that. All right, so this is roughly what the function looks like, and we're going to take a Laplace transform of that. So let's talk about it. So the Laplace transform of f at s, and remember, sometimes we'll write this as just capital F of s. It's going to be the integral from 0 to infinity of f of t e to the minus st dt. Okay, so if we want to go ahead and figure this out, what we need to do is we need to split this integral into several pieces. So I'm going to split the integral from, say, 0 to 1, and we have e to the t times e to the minus st dt. Then we're going to add on the piece where we have 0 to 5, or sorry, 1 to 5. And this is just going to be 5 e to the minus st dt. And then we're going to add on this last piece where it goes from 5 to infinity, and this is t e to the minus st dt. Right. So this is us expanding this across these the several pieces where we have our piecewise defined function. Okay. So now let's take a look. We have 3 pieces, and so why don't we just go ahead and integrate each one separately. So for the first one, we have the integral from 0 to 1 of e to the t times e to the minus st dt. All right. This is going to give me, say, the integral from 0 to 1 of e to the 1 minus st dt. And now we'll just do the integral. And so this is going to be e to the 1 minus s t divided by 1 minus s. And then this is evaluated at 0 and 1. And so at 1, what do we get? Well, when I plug in 1, I get e to the... so I get e to the 1 minus s, because t is what we're plugging 1 into. And it's divided by 1 minus s. And then we leave the 1 minus s there at the bottom. And then we subtract off what we get when we put in 0, which is going to be 1 on the top over 1 minus s here. Okay, so that's the first piece. All right. Now, the second piece, we have the integral from 1 to 5 of 5 e to the minus st dt. That's a 5, not an s. Let's not confuse that. All right. So again, let's see, 5 pulls out, and so the integral from 1 to 5 of e to the minus st dt. And then what do we get? We get 5 times e to the minus st divided by minus s, and value this at 1 and 5. And so we get 5 times e to the minus s times 5 divided by minus s minus e to the minus s, where we put 1 in for t, and divide by minus s. And I just want to make things look a little prettier, so I'm just going to rewrite this as e to the minus s over s minus e to the minus s 5 divided by s. Just redistribute, taking care of these minus signs and then swapping them around. Okay. So that was pretty good. Sorry for that cough. Now let's see if we can work out this last piece. So the last piece is the integral from 5 to infinity of t e. Ooh, that isn't just t, is it? It's t minus 5. So let me go ahead and correct that here before we really get into this. So we're going to have t minus 5 here. All right, so we have t minus 5 e to the minus st dt. All right, and now let's see. First thing, we notice that this is an indefinite integral, so we need to split it off into its limits. Limit as n goes to infinity of the integral from 0 to n, or sorry, from 5 to n now, of t minus 5 e to the minus st dt. Okay, now what we want to do is we actually want to use integration by parts. And so what I'm going to set is I'm going to set u is equal to t minus 5, which sets du is going to be just dt. And then we're going to have dv is going to be everything else. So it's e to the minus st dt. And that means that v is going to be e to the minus st divided by minus s. All right, so now let's multiply u, which is t minus 5, times v, e to the minus st divided by minus s. This is going to be evaluated at 0 and n, and not 0 and n, 5 and n. And again, don't forget to carry your limit over. So let's move this over, and we'll put limit there. So limit as n goes to infinity of this. All right, now back to the problem. So we have minus integral v du. So we have another minus sign we're picking up from v, so I'm going to flip sign there. And so it goes from 5 to n. And du is just dt, so all we're left with is e to the minus st divided by s. And remember, we moved that minus sign to cancel the other one. So instead of minus s, I just put s there. Then we're left with dt. Okay, so keep going. Sequester this off over here. And what do we get? Well, this is equal to the limit as n goes to infinity of, let's see, we put in n over here, so n minus 5 times e to the minus sn divided by minus s. Then minus whatever we get when we put in 5. When we put in 5, we see that t minus 5 is just 0, so that's just going to be 0 here. All right, and then we're plus, let's see, if we're just screwing around with parentheses, we need to distribute the limit. And so we have the limit here of the integral. What we get e to the minus st divided by minus s, and then squared not going on the minus sign. And then this goes from 5 to n. All right. So keep things going. Out of this first limit, I see that we have n minus 5 times e to the minus sn as n goes to infinity. Well, we know that the exponential is going to dominate, and so that means that this ends up going to 0. So that first piece there is just 0. All right, now plus the limit as n goes to infinity, and what do we get? Well, we have e to the minus sn divided by minus s squared minus whatever we get when we put in 5. So e to the minus s5 divided by minus s squared. And again, as n goes to infinity, this piece here is going to 0. So the ultimate result is that we get e to the minus s5 divided by s squared, where we combine this minus sign with this minus sign. Okay, so what is the Laplace transform we get? So we took the Laplace transform of this function, and which is written this way. Now, what that means is we take the integral from 0 to infinity of the definition of the Laplace transform, which is f of t times e to the minus st. All right, once we do that, but in order to do that, we basically need to expand the definition of what f is, which gives 3 different intervals that we're going to be integrating over. So we have this one from 0 to 1, then we have this one from 1 to 5, and we have this one from 5 to infinity. So we just performed the integrals for each one of these, here, here, and here. So now all we need to do is add them back together, and we get the Laplace transform for f. So that gives us capital F of s is equal to The first one is going to be e to the 1 minus s divided by 1 minus s. Let's clarify that a little bit. 1 minus s, there we go. And then we get minus 1 over 1 minus s. Now we need to add the next piece. So we get plus 5 times e to the minus s over s minus e to the minus s times 5 divided by s. And then finally we add the last piece, which is e to the minus s times 5 again divided by s squared. So we could, combine these two if we wanted to, but I'm not going to bother. Okay, so that is how you do a Laplace transform of a piecewise continuous function. You split it off into each individual pieces, and then you go ahead and you do each integral separately. So each one of these was actually pretty simple. Most of these ended up being just exponentials because we had exponential times exponential here in this piece, and then have a constant times an exponential. So those end up being pretty straightforward. Here we had t times an exponential, and so again that came up with this whole integration by parts coming in to eliminate the polynomial, or the linear function in this case. And more than that, this and this piece were just definite integrals, and so only one of them ended up being an infinite integral that we actually had to care about. Okay. So yeah, there we go. So yep, that is the integral of a piecewise continuous function. Let's move on. Okay, so now let's talk about the definition of a function of exponential order. So a function of exponential order is like this. So we have so a function of exponential, and I'm going to defer from the book here. I'm going to say of exponential type because that fits with a lot of other things. So of exponential type alpha, if there exists positive constants t and m such that we have this. The absolute value of f of t is going to be less than or equal to m times e to the alpha t for t bigger than or equal to big T. Right, so it doesn't have to always satisfy this inequality, it just has to satisfy it in the limit or for really large t. And so, yeah, so that's what you get here. And so what do we get out of this? So basically, we have a theorem out of section 7.2, and this is theorem 2 in that section. And what we get is that if f of t is piecewise continuous on, say, 0 to infinity, and of exponential type, or alpha, then LF of S exists for S bigger than alpha. Okay, so let's look at the different conditions here. So one thing we need is f is piecewise continuous. What does that mean? Well, it basically means that you can write it as a piecewise defined function where each piece is continuous. Okay, the reason why we have that in here is because that means that the Riemann integral is actually well defined. So so we keep that in there. And exponential type alpha, right? We just defined what that means. So f has to meet this requirement. And then basically we're saying that this exists. What does it mean for a Laplace transform to exist? That means the indefinite integral exists, right? So whenever s is bigger than alpha. Now remember, for each s we have a different integral. So that means that eventually, if we pick a big enough s, the integrals that we get when we use that s, they're going to exist whenever we're bigger than alpha. The whole proof is actually pretty straightforward. Basically, it's a comparison test. So what we're going to do is we're going to say we're going to Okay, so the proof of this is actually somewhat straightforward. What we do is we basically want to show that the limit as the integral goes to infinity actually exists. So if we take a look at the integral from 0 to infinity of f of t e to the minus st dt, and we want to show that it exists, we can break it up into two pieces. Integral from 0 to n of f of t e to the minus st dt plus integral from n to infinity of f of t e to the minus st dt, and we want to show that this guy goes to 0. This is the remainder term. Okay, well, it's not too bad. So basically what we do is we show, we just take a look at the absolute value, integral of n to infinity of f of t e to the minus st dt, and we can use the fact that moving the absolute values to the inside actually makes something bigger. Then we can use the exponential type property that f has, m equals 0 to infinity of f of t e to the, wasn't thinking for a second. Alright, so then this is replaced with e to the at times e to the minus st dt, and this itself is equal to 0 to infinity m times e to the minus s minus a t dt. And finally, we can integrate that. My integral bounds are all over the place, aren't they? No, that is not right. So erase these, erase these, erase this. Right, so this should be n to infinity, just to be clear, n to infinity, and n to infinity. Alright, now in order to evaluate this integral, what I need here is I need to turn it into a limit. So it's going to be a limit as n goes to infinity, not n now, but something else, say little b goes to infinity of n to b of e to the minus s minus a t dt, and we can go ahead and integrate this. So it's m limit b goes to infinity is the integral of n, now we just perform the integral. We have e to the minus s minus a t over s minus a, at the cost of a minus sign here. There we go. And if we take a look, we're evaluating this at b and n, so let's just go ahead and save a little time. It's going to be b e to the minus s minus a n all over s minus a. Alright, and that's a plus there. So as b goes to infinity, this term goes to 0, right? So that's going to be equal to m times 0 plus e to the minus s minus a to the n divided by s minus a. And again, I made another mistake. That shouldn't be a, that should be alpha. Again, easily corrected. Alpha, 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 alpha there, and alpha there. Sorry for the mistake. And now, if we take, now we see that this remainder term ends up being bounded as m times e to the minus s minus a n divided by s minus alpha, and this goes to 0 as n goes to infinity. And that tells us that this integral will exist. All right. All right. So what are functions that are of exponential type? Well, that's pretty simple. So every polynomial is of exponential type. And that's because basically if you have p of t divided by e to the t, this goes to 0, which means that basically at some point this is less than some quantity m, and so we could pick m to be anything, so we'll just pick 1 for instance. And so for p of t is going to be less than or equal over e to the t is going to be less than or equal to m, we'll say 1 for big enough t, which means then that we have p of t is less than or equal to m times e to the t, and there you go. So we have polynomials are of exponential type, exponential functions are of exponential type. And so is sine and cosine, etc. So most of the functions that we're ever going to be dealing with, they end up being of exponential type. And for sine and cosine, it's because they're bounded by 1. In absolute value. See. Okay, and so yeah, and I would like to add beyond this that the exponential type theorem is basically one direction. So we say that we have exponential type yields existence of Laplace transforms. But you don't need to be of exponential type to have a Laplace transform. So not exponential type does not necessarily mean that no Laplace transform. It might not have a Laplace transform, but you'd have to do a little bit more work. So in the book, they give you an example of something that's not of exponential type, and that'd be e to the t squared, for instance. This always grows bigger. So this is not exponential type. And so, and has no Laplace transform. So that is an example where we don't have an exponential type and we don't have Laplace transform. Demonstrating that there are functions that are not of exponential type but still have Laplace transforms, it takes a little bit longer. It's a little bit more fussy to prove that. So we won't really bother talking about it today. But yeah, I think that wraps up the section, I believe. And yeah, so if you take a look at the chapter and you take a look at section 7.2, you'll see that we have a whole table now of Laplace transforms. And these Laplace transforms, just really quick, let's write them out. So we have f of t, and they give us, say, the constant function 1. And last time we talked about it being 1 over s, and here we need s bigger than 0. We have e to the at, and remember that is 1 over s minus a, and here s had to be bigger than a. Again, this is both of these are of exponential type. T to the n, if you want to work it out, this works for n equals 1, 2, etc. We already have n equals 0. What we get then is we have n factorial divided by s to the n plus 1, and this works for s bigger than 0. All right. So again, polynomials are of exponential type, so that works. We have sine of bt, and we already worked this out. This is going to be over s squared plus b squared, right? And this works for s bigger than 0. Now we also have cosine of bt. You can do exactly the same thing where we do integration by parts, etc. We'll arrive at this formula slightly differently next time. S over s squared plus b squared, because we use properties of the Laplace transform, and we end up getting that. It turns out that you can, if you have a function and you have its Laplace transform, there's a slick way to get the derivative of that function Laplace transform using the first one. So we'll do that later. All right, so now let's talk about some of these other ones. So we have e to the at attached to t to the n, and this is for n equals 1, 2, etc. So this is going to be n factorial over s minus a to the n plus 1, and this works for s bigger than a. Now, what happens here? So take a look. So we have t to the n, which was n factorial over s to the n plus 1. But this one we multiply by e to the at, and now we get n factorial over s minus a to the n plus 1. When you multiply by e to the at, one of the properties we're going to see is that you end up shifting the Laplace transform. That's also how you get from here to here. And so you can, if you want, you can still go through and do integration by parts and do all the other stuff that you did back up here. But you can save yourself time once we learn the table of Laplace transforms to jump from this guy down to this guy, right? And the same thing works for these. So we have at times sine of bt is going to give us b over s minus a squared plus b squared. And we have e to the at times cosine of bt, and this is going to give us s over s minus a squared plus b squared, right? And so, and that's s minus a on the top. Let's fix that. So we get s minus a divided by s minus a squared plus b squared. And again, this whole table is in the book. And here again, we have s has to be bigger than a. Okay, so that's the table. And so what have we worked out explicitly so far? Well, we've worked this out, we've worked this guy out, and we've worked out this guy explicitly in the last video. So if you want to go and review it, that'd be good. And so what's left is we haven't figured out what t to the n is, and I'll show you a way to do that. Again, it's pretty slick, using the properties of the integral. We're going to work this out next, after the first one I just pointed out. And then we're going to get these two guys and also this guy. And all of these guys will fall out from the properties of the Laplace transform. So all you really need are these two guys. This one, and the rest you can build up out of it. Again, on the exam, you will have access to this table I just wrote down. And yeah. Okay, so we'll call it quits here and go back to my office.
Okay, so that's the definition of functions of exponential growth, and we also use a definition of Laplace transform to pick through the Laplace transform of piecewise continuous functions. So I think that covers it for section 7.2, and next time we'll do section 7.3, and I'll probably get that done tomorrow. Yeah, so yep, that's where we are today. You can see today I ended up being able to record in my home office, which is nice, and I can actually make some more quality videos this way. My wife is taking care of the babies, and she was kind enough to take them on a quick little walk, up and down the street, so that I get some quiet recording time, because no matter where I am in this house, I can always hear a baby scream. So yeah, I'm really grateful for that. My wife has been doing a great job supporting me. Anyway, but yeah, so I'll leave it at that, and talk to you tomorrow.